Okay. Now it's actually fairly easy to graph this if you know a couple of principles. One, you find the intercepts. That's what you do for any function. Probably the first thing you do in most cases. There's always an exception to the rule. I can't think of one right off the top of my head, but if I thought a little bit, I think I could come up with one. Find the intercepts. Okay. X-intercept occurs when y equals 0. Y equals P of X is 0 when this expression for P of X is equal to 0. This breaks into three equations. Because one of these being 0 makes everything 0. And if none of these is 0, it's not 0. So making a statement here that you should remind yourself of. And I recommend you write things out the way I write them out, showing all the logic, all the reasoning. X has any of these values, P of X is 0. That's easy to verify. You plug in any one of these numbers and you're going to get 0. Okay? We don't plug all three in. We plug this one in for all the X's, plug this one in for all the X's, plug this one in for all the X's. In each case, exactly one of these three will be 0, making the whole product 0. So if X has any of these values, P of X is 0, we can easily verify that. And if X has any other value, P of X isn't 0. In other words, if X is not 1, -2, or 4, then this isn't 0, this isn't 0, and this isn't 0. When you multiply a bunch of numbers that aren't 0 together, you don't get 0. You want to understand that. Otherwise, you're just imitating a method, which is not bad, okay? You can imitate the method without really understanding it, okay, but you're more likely to retain it and be able to use it in later courses if you understand it. So I emphasize understanding it. For this course, being a support course, just know that you can do this, but I still recommend you write it out like this because some of you are doing very well on the course and are capable of understanding at that level. Okay. Everybody's capable of understanding at that level, but you're capable of understanding it at that level without an extraordinary effort. Okay. Some people would require more time and effort than they have to understand it at that level. Not that they couldn't do it. Okay, so anyhow, there's what we know about the graph. So one thing we know about the graph is it goes through the x-axis at x equals -2, x equals 1, and x equals 4. Okay, well, y-intercept. Now, first of all, let's go ahead and mark these points. Okay, the y-intercept I was going to try to squeeze that in. Really got to get out of that habit. This almost never works. Y equals P of 0. And that means, of course, we plug 0 in for every x. Okay, so 4 times -4 is -16. Multiply it by -1, you get 16. Multiply it by 2, you get 32. So now we know on the line y equals 32, we have a point of our graph. And then if we're in a habit of graphing these things without thinking about them, we might graph like this. Okay. Okay. If we multiply all this out, we got an x here, an x here, and an x here. That's going to give us an x cubed. Okay. And that's what dominates the graph for large x. So I'm going to say that's 4x cubed plus lower powers. What does a graph of 4x cubed look like? Well, the graph of x cubed looks something like this, right? And we know that because we went into some detail of how you graph power functions. And that's something you definitely want to review a little better than what open math tells you, which is just basically plug it into a calculator. You want to understand the numbers. You want to understand why the graph flattens out like it does. So if you construct it or even plot it for x equals -2, -1, -1/2, 0, 1/2, 1, 2. And you do that for higher and higher powers, you understand how the higher and higher powers get flatter and flatter, and how the odd powers go up over here and down over here, because an odd power of a positive number is positive, an odd power of a negative number is negative. This is an odd power. If it was an even power, it was an x to the 4th, it would be flat, but it would kind of look like a flattened out parabola. And we need to understand that. We need to understand that numerically. We need to understand that in all kinds of ways. Okay? Because if you understand that, now we know that the graph looks like this. And then we've got a few little wiggles in here. And this is what the graph looks like if we zoom way back. But you see, it's got some wiggles in here that kind of do this. before it starts going up. Okay, you can't even necessarily see those wiggles. My point is, if you zoom way back, what you have here is going to be very small. So this tells you that it approaches this point here where it first reaches zero from way below. It goes up to this point, turns around, then it has to turn around so it can go up like this, because the x cubed graph goes up like this and down like this. Okay, and you don't have to do a bunch of numbers, although you certainly can, and it doesn't hurt to do that. I want you to see this in terms of the toolkit functions. This is dominated by this toolkit function. And you can convince yourself of that with some numbers. Okay. Now that's quite simple. Okay. It's a very simple exercise. You just have to know what to ask yourself, which is what you ask yourself for every graph. Where are the x-intercepts, meaning where's y equal to 0? Where's the y-intercept? Where's x equals 0? Yeah, where x equals 0. And then for a polynomial function, you have to look at the long run behavior. And if you have a given polynomial, it's easy to see what the long run behavior is. Just count how many x's you got. And then think about how the distributive law supports that. Okay, now I'm going to make it a little more complicated, just by way of review, because I think we did most of this last time. We want to move on. Other stuff you're going to need to know. Take the same. I'm going to use -2. X-intercepts are still at these points, right? This thing is of degree 3. Because x minus 1 cubed is the x cubed graph shifted horizontally 1 unit. So the rest of this stuff, if you're really close to x equals 1, all the rest of this stuff stays pretty close to whatever it is at x equals 1. If x equals 1, you've got what, 9 here, and -3, -20, so you got 54. So if x is close to -1, all the rest of this stuff stays pretty close to -54. Okay. But the x minus 1 cubed does the thing that a cube does. So if we want to graph thing this time, we've got an x equals 1. The graph is going to act like a cube. At x equals 4, it's degree 1. And that's linear. Y equals mx plus b has degree 1. Highest power of x is 1. And at -2, 0, The degree is 2. Long run. Is like negative 2 x to what power? You're going to get an x cubed when you expand this. So actually 3x is in this. I could write this as x minus 1 times x minus 1 times x minus 1, x minus 2 times x minus 2, and x minus 4. I could actually do that. I could go negative 2 times x minus 1 times x minus 1 times x minus 1 times x plus 2 times x plus 2 times x minus 4. And when I multiply everything out, this x will, among a whole lot of other things, eventually multiply this x. So I have an x squared, which then eventually multiplies this x, which gives you an x cubed, which multiplies this x and gives you an x to the 4th and an x to the 5th and an x to the 6th. Okay? Now we have a negative in front of this. So it's negative 2x to the 6th. The graph of x to the 6th is really pretty flat down here. And you can play around with it and see how flat, and pretty steep here. It almost looks like a U, but it never has, it's never quite vertical. It's always moving to the right a little bit, even though it's moving up like mad, okay? So this would be power 6. Well, this is negative 2 times power 6 because every y value up here is going to be multiplied by 2. And then because it's negative, it's going to come up over the x-axis, okay? So here's your long run behavior. Meaning it'll be down here and down here. Now the y-intercept I can label it up here. Well, p of 0, we just plug in 0. We're going to get negative 1 from the cube of negative 1. We're going to get 4 here. So we have negative 4 at this point. Multiplied by a negative 4, we have 16. Multiplied by negative 2, we get negative 32. Just a coincidence that comes out to negative what the last one did. This means we can sketch the line y equals negative 32. And then we've got to start down here because this is what the negative power of 6 tells you. And it's going to be down here because that's what the negative multiple of a 6th power does. So you're going to come up from down here. And this has degree 2. If you come up from down here and try to go through, you're not going to be able to get back to the x-axis without going through the y-axis on the wrong side. You got to go through the y-axis down here, not up here. But since it's degree 2, it's going to act like a parabola close to this point. So it's going to come down here, and then it's going to come down here, maybe a little bit lower, and then turn around and come up here. Now this is going to act like degree 3. That's like a cube function. come up here and it's going to level off. And it's going to go on back up for a while. Then it's going to turn around and come down through here. And now it's off to the races. And the graph's going to look something like this. This little foreshadowing, if you take any kind of a calculus course, calculus adds a little bit to this graph. The most obvious thing is calculus will actually tell you where this is and where this is. And it's pretty easy. So I could actually teach you to do that, but you have to be on the scope of this course, and you wouldn't have the context of the calculus course, so it wouldn't mean that much to you. But sometimes it's important to find the extreme values. Okay. How high does this thing go? If this is some kind of a manufacturing process that you're trying to model, and this is your profit function. Okay. And this is how much you're charging. Then you want to know what this point is, because that tells you how much to charge and how much profit you can expect if your model's right. Just one example. There are numerous examples that you'll encounter if you have a calculus course in your future. Okay. Well, that's all I'm going to say about that aspect of polynomials. If the polynomial is factored, you can always do this. Now, there's another thing that can happen. Yeah, I better mention this. One more possibility. This will lead us into the idea of factoring. This isn't completely factored. This is, because everything is a linear factor. Okay. What about x squared minus 5x plus 6? Well, that factors, it's x minus 2 times x minus 3. If you multiply that out, you're going to get x squared minus 5x plus 6. Now, you find where x squared minus 5x plus 6 equals 0, you use the quadratic formula. And we know how to use a quadratic form. It's very easy. Got to remember that. Okay. Not negative. There's no negative sign in front of the y. It's 3 or 2. Okay. So you know that this thing has to factor as x minus 2 times x minus 3. Because those are the numbers that make it 0. I mean, 3 makes this 0, 2 makes this 0. Okay. Now that's the harder way to factor, but it'll always work. Understand the logic of that? Okay. If you multiply x by x, you get the x squared. And if x is 3, this is 0. And if x is 2, this is 0. It has the same zeros and it's a square. It's constrained. It has to be a shifted quadratic function. with those zeros. Okay, well, the reason I mentioned that is let's try that on this one. You know, I messed that up. That's nothing. One x squared plus 6x plus 7. Because this one would, the one I had up there would give you zeros. Okay. Thought this one would give you 0, but 4 I see it's still too big. So apologies. Make assumptions without thinking it through. Okay, now this is going to work. Okay. It's going to show you what I want to show you. I'm sorry. I apologize for messing that up. Now I've left out all the details, some of the details, but you know how to use a quadratic formula. And you can verify this very easily. You got a square root of -4 there. What's that mean? That means there's no real number that makes this 0. Okay? No real zeros. X squared plus 6x plus 10 can't be factored using real zeros, using real numbers. Okay? We call it irreducible. So this factors, this is irreducible. So we can't write it in factored form, at least not until we get to complex zeros in another week or so, probably next week sometime. It's an irreducible quadratic. Its graph never touches the x-axis. This graph stays above the x-axis in this case. All right. Well, the fundamental theorem of algebra tells you that any polynomial, any real valued polynomial, but that's all we're dealing with, any polynomial can be factored into, on real numbers, into linear factors. These are both linear factors. And, 5x plus 8 would be a linear factor too. Just any linear expression, any expression that would have a straight line graph. Factors into those and irreducible quadratics. Okay. Well, the reason I mention that is because that's what we're going to do. We're going to see how to factor these things. So let's say used up that board space, haven't I? Okay. Let's say you have P of X equals X cubed plus 6X squared minus 5X, okay? And minus 2. Okay. Try to find a 0. That means a number that makes this 0. Generally try maybe -1, 1, -2, 2, -3, 3. Those numbers, just plug them in. If you plug in -1, do you get 0? Well, if you plug in -1, you're going to get a -1 there, right? But your 6x squared is going to be 6 because -1 squared is 1. And -5 times -1 is 5. 6 and 5 makes 11. You got -1 and -2 for the first and third. Okay. So all I'm saying is in your head, just about, you can do this. You can always plug it in, do it on paper. But I can see right away that since -1 squared is 1, I'm going to have 6 from this. And 5 times -1 is 5. 6 and 5 makes 11. Okay. Well, this is -1 and that's -2. So we got 11 and we got -3. It's clearly not 0. The positive numbers we get here are way bigger than the negative numbers we get here. Okay, well, let's try the rest of them. Let's try 1. Plug in 1, see what you get. That's bad. Okay, so everybody got that quickly. P of 1 equals what? 1 plus 6 minus 5 minus 2 equals 7 minus 7 equals 0. Check. Okay, now why is that good? This means first of all, that x minus 1 is a factor. I mean, think about it. If x minus 1's in there, then your 0 is going to be at 1, right? Okay, so, we could immediately say, well, let's see, x equals 1. We can immediately write the x-intercept at 1. So by trying these numbers, we've found an x-intercept. And while we're at it, before we see what we do next with the factoring, we say, well, if x equals 0, it's pretty clear that we're going to end up with -2, right? Because all the rest of these terms are going to be 0. So we know that at y equals -2, we have a 0. Now, I don't know if there are more zeros or not, but the other thing we know is that the long run is dominated by x cubed. So zoom out. We get a good old x cubed graph, right? So we know that thing's got to go down here. It's got to go up steeply here. So maybe the graph just comes up through here, comes up through this point, turns around and takes off. That's possible. But we don't know yet. Okay, so what do we do? Just making the statement, since x minus 1 is a factor, we know if we divide this by x minus 1, ultimately, the x minus 1 here will divide the x minus 1 of whatever this thing factors out to. Maybe that's not a very clear statement, but it says that this will divide this with no remainder. For example, with numbers, 5 is a factor of 40. If we divide 5 by 40, we get 8. We don't get any fractions, right? We get no remainder. 5 is not a factor of 41. If we divide 5 into 41, we get 8 and 1/5. We get 8 with 1 left over. Okay? So in an analogous way, it's going to work with this. And there's a procedure for doing this division. It's just like the long division you learned in 5th grade. Except it's different. It's just like it, except it's different. It's very similar. It's analogous. So we're going to do this like so. We're going to write out x minus 1 divides into x cubed plus 6x squared minus 5x minus 2. Now, if it divides into this, since x divides x cubed and leaves x squared, we're going to have an x squared term out in front. Okay, so we just look at this and say, well, x divides into x cubed, leaving us x squared. X cubed divided by x is x squared. Then we multiply x squared by x minus 1. And what this tells us, the reason we do this is, once we have an x squared out here, we're going to have x cubed, okay, x minus 1 times whatever we get up here has to equal this. This tells us that so far we're good because x squared times x minus 1 is going to give us an x cubed. That's all the x cubed we need. It also gives us a negative x squared. So what have we got left? If we've got x cubed minus x squared, how much of this do we have? Well, we have, let me get my chalk here. Turns out we have seven x squared minus 5x plus 2. In that, if we add this to this, we get this. Can you verify that? 7x squared added to negative x gives us 6x squared, right? And the negative 5x gives us negative 5x, the negative 2, that's negative 2, I wrote that wrong. Okay. And we've already got the x cubed. So if we add this to this, we get this. Now, it's good to remember that, but there's a procedure we follow. How do we get 7x squared out of 6x squared and negative x squared? Well, we subtract the negative x squared. If we subtract negative x squared, that means we're really adding x squared. So I'm going to put a little plus here to remind myself, I'm not subtracting x squared from 6x squared. Okay. I'll actually be adding x squared to 6x squared so that what I get down here added to this still gives me this. And then, of course, x cubed minus x squared, well, that's a minus. And that gives us 0, so we don't have to write it down. Okay, so the main thing about it is, well, let's just do it. Okay, if we divide x into 7x squared, what do we get? We get 7x, right? 7x cubed over x is just 7x. So we have plus 7x. Meaning that, ultimately up here, we want to get something that multiplies this to give us this thing under the division sign. That means that this 7x will be multiplied by the x minus 1. So we write out 7x squared minus 7x. Okay. And then we put a little plus here, a little minus here to remind us that we're going to actually be, we're subtracting this. We're actually going to add 7x to negative 5x. It's going to give us 2x minus 2. Okay. Now, how many times does x go into 2x? 2. You multiply 2 by x minus 1, you get 2x minus 2. You're done. No remainder. Okay. I didn't know what this was going to come out. I didn't choose it. All I did was I wrote down 3 terms here and then said, okay, I want the 0 to be 1. So let's say x is 1. This adds up to 2. 1 and 6 and negative 5 and give me 2. So I subtract 2. And now I know that x equals 1 is going to give me a 0. That's all I did. Didn't do anything clever at all. Okay. So okay. To get the zeros, then in this form, we got this times this equals 0. Now there's a linear term. And of course, this equation breaks into x minus 1 equals 0, which is easy. So x equals 1. We already knew that. But over here, we get x squared plus 7x plus 2 equals 0. Can you factor that? I don't think it can be factored. Matter of fact, I know it can't be factored. I mean, never mind. It can't be factored over integers. There's no whole numbers that will factor this. So what do? What we did, what I showed you before, we used the quadratic formula. Now, I didn't write out the details, but if you write out the details, unless I made a terrible mistake, x would be -7 plus or minus the square root of 53 over 2. Now, the square root of 53 is about 7.3. Which gives us about 0.15 or 7.15. And this one gets a little dicey to graph, but not that badly. Okay, so where are our zeros? X equals 0.15. Going to be about here. And x equals 7.15, maybe out about here. That's assuming I did all the quadratic formula correct. I did it in my head, but I think it's probably correct. So what's going to happen here? Got to go through this point, this point, this point, and this point. Every one of them linearly, because all these zeros have degree 1, multiplicity 1. So we draw the graph. We just come up through here, pretty steep right here. It's got to turn around at some point, probably pretty quickly. It's got to go down through here. Then it's going to go down a ways, and then it's going to turn around and come back up through here. So it's not much different from anything else that we've seen. The new thing is we had to do a little work to find the zeros. We got lucky and one happened to work. We can't always count on being lucky. We can't always count on finding one. And then there are approximation methods we can use. And we don't bother with those now. Because the best approximation method is probably Newton's method, which is a calculus method. I mean, there are even better ones, but they're more complicated. So that's kind of where we are. Okay, now there's an assignment on factoring monomials and trinomials. Okay, factoring with monomials and factoring trinomials. I'm not going to talk much about that because my experience is people usually by doing the assignment do that fairly well. It's something that people usually do learn to do pretty well in high school. It's one of the few things that people come out sort of remembering how to do. Okay. If I find I'm wrong, then I'll go back and do it and talk about it. So if anybody has a big problem with it, let me know. But I want to move to rational functions. Form of a rational function is P1 of x over P2 of x. And these are both polynomials. I'm going to start with a pretty simple one. I'm going to start with r of x equals x plus 3 times x minus 4 over x plus 1. The procedure. Find the zeros of the numerator. And we do that very easily since the numerator is already factored for us. So we can start building a graph. So at x equals -3, we have a 0. At x equals 4, we have a 0. Find zeros of the denominator. Well, that happens when x is -1. Very easy. If the thing is factored. If it's not factored, then you factor it, if possible. Okay, so we got x equals -1, but that's not going to be a 0 of the function. When x equals -1, x plus 3 times x minus 4 is about equal to -12. So it's almost like -12 over x plus 1. So I'm just going to claim now, why don't I write 1 for this? Well, that would be 0. We can't divide by 0. And the point is, when x is changing near x minus 1, it's never actually equal to 1. I'm sorry. When x is changing near x equals 1. Now it's x minus 1. It's supposed to be x plus 1. Right there, I could have seen it. Okay. Again, when x is close to plus 1, like 0.99, 1.01, numbers real close to 1, then these numbers are real close to -12. And they don't change much if you keep x really close to -1. So y equals -12 over x plus 1. What's that graph look like? Well, that's just a reciprocal graph. Just that little note that says it's a reciprocal graph reflected about the x-axis. I didn't want to take the room to write about the x-axis, but we know that negative reflects the reciprocal about the x-axis. Vertically stretched by factor 12 and horizontally shifted -1. So it's like we take a stretched reciprocal graph, which might look like this. Okay. And we shift it over so that the asymptote is not the y-axis, but the line x equals -1. So we shift this over, we shift this part over. And we get something that looks like this. Close to -1. Now it's going to level off somehow, but that's a vertical asymptote at x equals -1. Does that make sense? Now you have to understand the whole shifting and stretching, the whole transformation. Process to understand what I just told you. But the bottom line is when x is -1, this is close to 0. When this is close to 0, when you divide into whatever the numerator is, we're going to get something really big. This is close to 0, this isn't. In this case, this is close to 0, this is close to -12. Okay. When you divide a tiny number into a number that isn't tiny, it takes a lot of the tiny number to make the other number, which means your quotient is very big. Okay, well, so there we have it. The other thing is, and let's see what the time is. Okay. Long run. The biggest power in the numerator is 2. The biggest power in the denominator is 1. So the long run gives us something like this. Something like this. That maybe this is shifted up or down a little bit. That makes sense in terms of what we've talked about. So to find out exactly what this line is, if I multiply x plus 3 by x minus 4 using the distributive law, I get x squared minus x minus 12. Okay? And I'm even going to write that out here so I can actually refer to x squared minus x minus 12 over x plus 1. We haven't needed that until this point, but now I want to find out what the straight line is that this graph approaches. So I divide this in here. I get x squared plus x. Be careful to write a minus here and a minus here. So I know negative x minus x is negative 2x. And then it's minus 2. And minus 2 times this is negative 2x minus 2. It's actually like a plus. This is like a plus, giving us a remainder of negative 10. So this becomes x minus 2 plus negative 10 over x plus 1. That makes sense? It should, because we've been through the long division. The straight line is x minus 2, y equals x minus 2. So let's put some y values on here. The y-intercept is at negative 12 over 1. So the y-intercept is that y equals negative 12. The line y equals x minus 2. Well, y is negative 2 about here. And x equals negative 2 would be about here. It would go through this point and this point. We call this a slant asymptote. So what the graph does is from the left, it stays close to this asymptote. But it's got to approach this vertical line as another asymptote. So it comes along here and stays along here, but then diverges a little bit. It comes down here and does something like this. Does that make sense? Open Math is going to walk you through it a little bit. Over here, it's going to come down from here, but it can't keep coming down because it has to approach this line as an asymptote. So it's going to do this. So what's happened is denominator being 0 when x equals negative 1 means you have a vertical asymptote at x equals negative 1. The fact that this is x minus 1 as opposed to like x minus 1 quantity squared. In other words, this 0 has degree 1 means it just acts like a regular reciprocal function around this asymptote, close to it. So it's asymptotic here, it's asymptotic here. It has to curve away from that asymptote to approach this slant asymptote. Now, there's another problem I've got, and it's a kind of a serious problem. What's going on here? I have a 0 at x equals negative 3 and a 0 at x equals 4, so that can't be right. So that's kind of what we do, the asymptote, but I've missed my zeros and I've missed my y-intercept. And the reason I've missed my y-intercept is I graphed this like the reciprocal function, not like the negative reciprocal function. I didn't flip it across the axis. So I missed my known points. This graph has to go through these points. So that blue graph, pretty as it is, we'll just kind of wave it out and draw another color. It comes up from down here, goes through this point. And because of -1 plus 3 times -1 minus 4 being negative, it flips the reciprocal graph around so it can do this, and then it can come up through here and up through here and approach this asymptote. Okay. So I actually made that mistake because I wasn't paying attention. And I saw just such a beautiful curve in here. This curve isn't nearly as beautiful, but this curve is right. Okay. I was misled by my aesthetics. Okay. I'm too old to do that. And there we go. Okay.